Welcome to Ready to Derive. In this video, we are going to be continuing our study of U-substitution as applied to definite integrals. This builds on my first video on U-substitution with indefinite integrals, and you should watch that first for sort of more detail on the steps. I will link that video in the description. In that video, we took what looked like a complicated composite function, and using U-substitution, we realized that we just in effect are reversing the chain rule to get this. So if you took the derivative of the right-hand side and applied the chain rule, you would get the integrand on the left. In this video, we just introduce a lower and upper limit, and by the fundamental theorem of calculus, you could say, well, that's just the antiderivative of evaluated at b minus the antiderivative at a. That looks kind of complicated, and by replacing g of x with u, we actually really make this look a lot less complicated. I will begin by reviewing U-substitution as applied to indefinite integrals using the very same example that I used in my first video. But without further ado, let's begin. So we'll begin as promised with a review of how to evaluate an indefinite integral by U-substitution. So the first step is to define u to be the inside function, g of x. So we see cosine of x squared as our composite function, so x squared must be the inside function. So we will let u equal x squared. That's define. Differentiate, du by dx equals 2x. And then at this point, I often like to isolate the du. Sometimes we need to tweak that a little, but for now, let's work with that, and we can see, first of all, I'm going to sort of rearrange this. So I would like you to see that if I move the 2x closer to dx, then we see 2x dx. Oh, that's convenient. That can be replaced with du. And then we also have x squared, which can be replaced with u. So we are ready to go to step 3, which is to convert everything in terms of u, which I call u-land. So this will be cosine of u, and then 2x dx is just du. At this point, we're ready to find the antiderivative. No more composite functions, just a straightforward antiderivative. So that would give us sine u plus c. But clearly my answer, if I look at the beginning, I have something in terms of x, so my answer better be in terms of x. So let's not forget the next step, which is to back substitute. So I'm going to replace u with x squared, and that would be my final answer. But now we are going to turn this indefinite integral into a definite integral by adding some limits. So now we are basically asking for the area under this function between 0 and rad pi over 2. And we realize that by the fundamental theorem of calculus part 2, if we could just figure out that antiderivative, we could then evaluate it at the upper and lower limits and subtract. So I'm going to just carry this down. I'm not going to keep rewriting the limits because that's boring, except here at the very end. So 0 rad pi over 2. Now I am at the situation where I can apply the FTC part 2. So we get sine of radical pi over 2 squared is just pi over 2 plus c minus sine of 0 plus c. And I hope that you see, oh, pardon the overuse of c's, but I hope you see that the c's cancel. And we are left with sine pi over 2 is 1 and sine of 0 is 0. So that's our final answer. And I just want you to take a look at what we actually just figured out. So that is the graph of the function 2x cosine x squared. It's a really fun function. It's periodic, but it's also expanding in amplitude, so to speak. And we are focusing in on this little portion right here. We're going to zoom in on that. So let's see, if we zoom in on that, we are finding the area of that blue region. And I find it striking that the area of that is just 1. So perfect. You know, we've got like a crazy function, we've got radians, we've got, and the area turns out to just be 1. I think that's what makes math so wonderful. So here's the same problem, but expressed as a definite integral, and we'll follow some of the same steps. So we define u to be the inside function, u equals x squared. We differentiate, that stays the same, du by dx equals 2x. And then I always isolate du. And then we get to this next step. So we are going to substitute and turn everything into u-land, but this includes the limits of the integral. So if we realize these are all in terms of x, the lower limit is x equals 0, the upper limit is rad pi over 2. So upper limit, x equals rad pi over 2, and we know that we need to turn this into u-land, and u is x squared, so u will just be pi over 2. And for the lower limit, which was x equals 0, u is x squared, 0 squared is just 0. So now we can make the substitution, but we're going completely into u-land. So now u goes from 0 to pi over 2. Remember from before we had cosine u du. And then we're at the step where we can evaluate the definite integral, but using the fundamental theorem of calculus. But remember now just because we're in terms of u, I mean, we could have just replaced now u with x or even with y or t. It doesn't matter. It's just we need to do the antiderivative. So we get sine u. But notice now we do not have to back substitute. So we just have to evaluate it. So sine u is pi over 2 minus sine 0. Sine 0 is 0. Sine pi over 2 is 1. And we see that that is a much more efficient process. So our first practice problem will do something a little more straightforward. This could be done without the steps of U-substitution. It could be done a little more intuitively because pi x over 4 is just a linear function, that inside function. But we'll go through the steps just to demonstrate. So step 1 is to define. So u equals secant squared of the inside function is pi x over 4. So du by dx is pi over 4. And isolating du for the time being, we may need to manipulate this a little further, we get that. And so I'm going to start to sort of substitute in, turn it into u-land step by step. So we can write secant squared of u at least. But notice that we actually have dx just alone. We want dx alone. We don't want the pi over 4 there. So the best thing to do is to isolate dx. I'm going to bring the 4 over pi onto this side with the du, and that now can replace for dx. So 4 over pi du. And now I need to work on the upper limits and the lower limit. So the upper limit is x equals 1, and if I plug that in, then u is pi over 4 times 1 is just pi over 4. For the lower limit, x equals 0, u will just be 0. So now I can go and replace those with 0 and pi over 4. Now I have finished step 3, and I'm on to step 4, evaluate the definite integral. So I think I'm going to bring that 4 over pi, that's a constant, I'm going to bring that outside. I could have brought that outside the integral, and therefore I will bring it outside of the antiderivative of secant squared, which is tan u, going from 0 to pi over 4. So 4 over pi times tan pi over 4 minus tan 0, according to the FTC part 2. Tan of pi over 4 is 1, tan over 0 is 0, and we get left with 4 over pi. And that's our final answer. So for the second practice problem, let's have a look here. It looks like x squared plus 2x plus 2 is the function within the function of cubing. So that's what our u is going to be, x squared plus 2x plus 2. So second step, take the derivative, 2x plus 2. And I'm already anticipating, because I see an x plus 1 there, that I might just factor this here as 2x plus 1. And then let me isolate du, 2x plus 1 dx. So I can begin to make the substitution. So I know that I'm going to have 1 over u cubed. And I see actually that I have x plus 1 dx. So I could rewrite this and get that x plus 1 closer to the dx, but saving a little time, I see that I'm going to have to get x plus 1 dx and get that 2 to the other side, so half du. So I'll make that replacement with half du. And then I just have to work on the upper limit and the lower limit. So the upper limit is x equals 1. And that means, and I plug that in, sorry, that's not u squared. What am I doing here? U equals, so 1 squared plus 2 times 1 plus 2, which equals 5. So that's my upper limit. And then with x equals -1, I'll let you figure that out, and that will be, u will come out to be 1. So I have converted this to u-land, and I'm going to factor out that half. And it's a good idea, we're going from 1 to 5, if I probably should rewrite 1 over u cubed as u to the minus 3 du. And then keeping that half out there, factored out. The antiderivative of u to the minus 3 is u to the minus 2. And I mustn't forget to compensate with a -1/2 there. So that's the reverse power rule from 1 to 5. I think I'll take out that -1/2 outside. So we have -1/4. And I'm going to rewrite u to the minus 2 as this because it's much easier. 1 over u squared is much easier to plug in that form. And so we have the -1/4 outside. And we have 1 over 5 squared, which is 25, minus 1 over 1 squared is 1. And if you do all the fractions, take care of all the fractions, you get left with 6 over 25. Which is our final answer. So for our third practice problem, we're in a situation where it's not clear what to make u equal to, because just to sort of backtrack, remember we are looking for composite functions. So composite functions of the form f of g of x, and we usually define u to be the g of x, which is the inner or inside function. But what is the inside function here? Ln x is not a composite function to begin with. If it was ln x cubed, yes, x cubed would be the inside function. X is not a composite function, although it is in the denominator. And if you think about sort of a function like 1 over sine x, that would be a composite function where the inside function would be sine and the outside function would be 1 over. So let's try this, and you're going to sort of see why you never want to make u equal to x as your inside function. So I'm going to take you down, like I said, that's sort of dead-end road right now, and to see why this wouldn't work. So if we went through these steps and you try to start to make the substitutions, dx would be du. Well, we made xu and we made xu, and you see that you'd be actually at the same, basically at the same situation, but with u in place of x. So never make that substitution, u equals x, because you're not really solving any problems. So there's only one other thing we can do, is hope for the best that if we make u equal to ln x, this works out. So du by dx would be 1 over x, and du would be 1 over x dx, which I am sensing I'm going to break this apart at first to sort of see what's going on. So ln x is here, and I can pull apart 1 over x dx. All right, so that's looking promising. So in fact, I'll leave those limits there, and let's just replace ln x with u, and 1 over x dx with du. How perfect that is. Okay, and the upper limit, so when x equals e squared, u equals ln e squared, which equals 2. So we'll put that for the upper limit, and for the lower limit, when xn equals e, u equals ln e, which equals 1. So now we are we've completed step 3, and we can just evaluate the integral. So the antiderivative of u is half u squared, and then we just plug in. So half of 2 squared minus half of 1 squared equals 2 minus a half equals 3/2. So for our last practice problem, we'll take on a slightly more challenging problem. only slightly, but very important to see this scenario because it's not uncommon for sure. So what is the composite? What is u going to be defined as? Well, we clearly have, here's the composite function. Square root is the outside function, 2 minus x is the inside function. So let's make u equal to 2 minus x. So du by dx equals -1, du equals negative dx. And as we begin to make these substitutions, so I'll leave the limits aside for a moment. So radical 2 minus x is radical u. Now notice we just want dx, so let me get the negative to the other side first. So dx is going to be replaced with negative du, but we have a little issue here because usually we're not left with any other terms, but we have an x minus 1 situated here. So what are we going to replace that with? Well, here's where you need to get a little creative and realize that you can find an expression for x minus 1 in terms of u. If we just, let's see, if we just rearrange this, bring x to the left side and u to the right side, we would get that. And then x minus 1 is just going to be 2 minus u minus 1, which is 1 minus u. So this x minus 1 just gets replaced with 1 minus u. Now, for the upper limit, x is 2, which means u equals 2 minus 2 equals 0. So we'll put that there, 0. And the lower limit, x equals 1. So u equals 2 minus 1, which equals 1. Now, that negative here, I'm going to bring that outside the expression, the integral. And you have to realize that this product, you have to distribute first in order to be able to take the antiderivative. And while I'm at it, I'm going to use exponents. So square root of u is u to the half. So we would get u to the half minus u times u to the half would be u to the 3/2 du. I hope you realize by the property of integrals, but that if we're not used to going from 1 to 0, a higher number to a lower number, so we can flip this and make this 0 to 1. That would remove the negative of u to the half minus u to the 3/2 du. Kind of technically, you could put parentheses there if that helps. And then we just do the antiderivative. So 2/3 u to the 3/2 minus 2/5 u to the 5/2, right? The reverse power rule from 0 to 1. And luckily 0 plugged in gives 0, so we just have to worry about 2/3 minus 2/5. And if you do the fraction work, the answer comes out to 4/15. So well done for making it to the end of the video. Here are 3 problems involving U-substitution for you to try. If you put the answers in the comments, I'll be sure to let you know if you're correct. And please do subscribe to my channel, Ready to Derive, and check out some of my other videos. Thank you.